Yeah, good day, everybody. This is the third video on mean values on this course, mathematical methods, and this morning we would finally be discussing the proof of mean value theorem. Last class, don't forget we talked about we discussed the proof of the Rose theorem, and this time around we are looking at the proof, the final proof for this chapter, which is the proof for the um, mean value theorem. So here you are going to see how the Rose theorem comes to play in this proof. Okay, so I'm going to have to, of course, to refresh our memory. I would have to state the mean value theorem again, which says, okay, it says let A be less than B strictly, and F be continuous on closed interval AB and differentiable on open interval AB. All right. If that's the case, there exists C between A and B such that the derivative of the function f at C will be fb minus fa over b minus a. So that's what the mean value theorem is saying. But then before I proceed to proving it, I would like to, because it doesn't really make any sense if we say we are proving something and you don't even know the essence of what you are proving. You don't even understand what we are proving. These are the things that lead students to cramming. So let's show what we are talking about. Uh, say we have this Cartesian coordinates. So we have this function. Okay, we have a point here called A, we have a point here called B. Then we have this function that spreads out like this, beautifully like that. So here we can trace this one up to this place and call it, move it to this side and call it f of A. Sorry, f of A. Okay, let me, that's looking untidy. Excuse me. Give me a second. So we now have this place to be f of A. All right. So we can trace this place up, and we come here, and we have it as f of B. All right. So the gap between the two, from here to this place, that's definitely is f of A, f of B minus f of A, and the gap between this place, this going to be B minus A. Now, if we take a line, a straight line, if we draw a straight line between the 2 points on the curve, let me pick a different color so as to make it much more attractive. Let me try this one. I've not used this one before. Okay, so if we draw a straight line between it, okay, so my straight line would cut like that. Okay, let's assume that's a straight line. It's not that straight, but then, hey, okay, so that's a straight line. Okay, fantastic. If we draw that straight line, the change along the x-axis of this straight line, let me pick another color, so red this time. So the change along the x-axis here of course, is a B minus A. And the change along the y-axis here, and that's going to be f of B minus f of A. All these things are quite obvious. There's not much mathematics there. So if we are now looking for the slope of that straight line, apparently that's going to be f of B minus f of A over B minus minus A. Okay, so that's going to be the slope. We can call that m. All right. Now, what the mean value theorem is saying is that if you have a situation like this, then there will be a point C. Let's call this place C along this, such that when you trace it up, it's going to, then the tangent that you can obtain from it is going to be parallel to the line that you just drew. Meaning that if it is parallel, then it means that it's going to have the same derivative. That's what they mean. So here at this place, we are talking about the y, change in y over change in x of a straight line. And of the curve, we are now going to be saying that the derivative at point C will be the same thing as m, which is the same thing as f of B minus f of A over B minus A. That's what it's saying. That is, if what it's saying generally is that if you have any curve that is wavy, then and you pick a secant, which is a point, I mean a line that crosses, is a line that crosses 2 points on the curve. Then there must be a point on the curve whose slope or gradient will be parallel to the secant that you have done. That's exactly what it's saying. So in 100 level, don't forget what I said. I said differentiation is nothing but you measuring angles. So what it's saying technically is that the angle here would also be the same angle here, and the angle okay, let's say this is theta 1 and this is theta 2. We are saying that theta 1 will be the same thing as theta 2, and this theta 1 that we are talking about, we can obtain that using tan theta, that is tan theta. So we can say tan theta 1 will be tan theta 2. And what's tan theta 1? That's change in y over change in x. All right, which is what leads to derivative. So that's what the whole uh, mean value theorem is trying to say. That is, a secant, which is a line that crosses between 2 points on the curve, would be parallel to a gradient, at least one gradient on the curve. That's what the mean value theory. So I'm saving this page, which I'm going to send to you later. I hope that you understand that thing. Apparently, the way it's appearing, it's like I still need to sketch that drawing, because that's what I'm going to use to explain the proof. I want the proof to be as straightforward as possible. So so let's draw it. Then so I'm going to sketch it again, since I can't be going forth and back looking for where I've drawn it, so it's better. So it's going to be like this. The stupid people, they have taken their lights. So, and this place looks kind of dark now. So if this is A and this place is B, then this is going to be FA, and where's my B? It's going to be FB, kind of. All right, so let's just assume that. Excuse me. Okay. Okay. think the gen is on. Just give me a moment. I think let me take that time to clear the board and redraw. While I wait the light to come back, let me redraw. Yeah, light is back. Okay, so it's going to be okay. This one comes up here. It's like good. I bet the ruler. All right. This one comes like this, and we have A here. We have B here. Then we are trying to draw a curve that will transcend both of them. So if this place is like this, then this FA. Let me extend this one and call this one B. It's going to be livelier if I do it like that. Okay, it means this is going to be FB at that point. Okay, so we are saying if we draw a line, any line that is going to connect these two coordinates, then that line will be parallel to something somewhere here. Of course, there are even 2 points that is parallel to. So here we call this place, obviously that's the coordinates. This is B comma f of B, and this also is a coordinate which is a comma f of a. All right, so that's practically everything we need for the proof. So now let's talk about the proof. The proof, I can assure you this is going to be probably the most exciting proof you will do throughout your days in this school. It's actually quite funny. So, well, F satisfies the hypothesis of the mean value theorem, as in the F we're talking about. All right. So, um, that is F is continuous on AB. F is that's point one, point two. F is differentiable on AB. Okay. So, and of course, A is strictly less than B. So we have all those conditions. Now, we have drawn a line, a straight line that is connecting 2 points. So if we go back to 112, as in MTH 112, we talked about the equation of the line. So from the equation of the line, from the equation of a line passing through 2 points. So when you were in 100 level, I told you that this equation is extremely important. And now here we are using it. That equation generally says y minus y1 over x minus x1 equals y2 minus y1 over x2 minus x1. That's the equation of a line passing through 2 points. So we are now applying it here. We know the line that we talked about passed. So the line that the seconds that we talked about passed through. So since the second passes through, it passes through AFA and BFB. Therefore, we can apply this law to it. It means that this is going to be x. This is going to be f x. Sorry, this is going to be x1. This is going to be fx1. This is going to be um, x2, and this is going to be fx2. So we can put everything together in this place, and we are going to have y minus, what did I say y1 is? Okay, all right, 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 all right. I've made a couple of mistakes. This is a y1, which is the same thing as y1. This one will be the same thing as y2 on a normal day. So this is going to be y minus y1, which is going to be fa over x minus, of course, x. Okay, fantastic. X minus a, since x1 is the new a, and it's going to be equal to y2. That's going to be, what's my y2 there? That's fb, and then my y1 is fa, and x2 minus x1, that's going to be b minus a. So you can see now, when I was telling you in 100 level that nothing we did in those classes will be lost, we can see now here we are applying it. So let's make y the subject of this formula as quickly as possible. So I'm saving this page. We know where we are making y the subject of the formula. If you run into any problem, you can just put back the video and review it. So I don't anticipate that there will be such problem. So I'm dividing my page into two, and I'm making y the subject of formula now. This implies that if you are making y the subject of formula, this will be y equals y minus fb over, okay, sorry, this will imply, okay, sorry, let me just clear the canvas. Okay, so this is going to be y equals fb plus x minus a times fb minus fa over b minus a. All right, don't ask me how that is so. It's actually quite straightforward. I'm trying to minimize my screen. Okay, it's actually quite straightforward. Just do cross multiplication of some sort. It's not okay, yeah, and move stuff around. So you are going to get to that point. So now, okay, so that is our y1. Of course, y1. Uh, let's now subtract. Let's do some interesting subtraction, because this y is representing a straight line, okay, but f of x is not a straight line. That's this y is the second line that we talked about earlier, and f of x is, so let's subtract the two functions. Let's subtract f of x from the straight line. We know that the straight line is a continuous function, so since we know that we drew it all the way, so we have no problem with that. So now let's talk about, let's define gx. We are defining another function now. Define gx as gx equals f of x, that is the curve, minus y, the straight line. Okay, we are subtracting the curve now from the straight line. So this is going to give us the same thing as f of x, which is the curve, minus y, which we just defined there, which is f of b plus x minus a, all right, times fb minus fa, everything over b minus a. Okay, yeah, that's the way that is. So we are doing that multiplication. Please, at this point, I would suggest that you go as slowly as possible. All right, now let's talk about G. Okay, let's talk about G. Okay, let's talk about G. I think, okay, let's talk about G. Let's talk about gx of G, the function G. Is the function G continuous? Is G continuous on AB? That's the first question I'm going to ask. If it were in a class, I would have awarded some, generous mark for that. Yes, that's the answer. Answer, yes. Why? Of course, I would have asked. Okay, the reason is this. When you had continuous functions, you get continuous functions. All right? And f of x, we have established that it's continuous. All right? We've established earlier that f is continuous. And this straight line we just drew, since it cuts straight from across the entire uh, f of x curve, then it's also continuous. So when you subtract two continuous functions, you get a continuous function. And you know that we got gx by subtracting the secant from the curve. And the secant is a continuous function. The curve is also a continuous function. So definitely their subtraction is continuous. Why? Fx, sorry, f is continuous, and is and y is also continuous. And the difference of continuous functions is continuous. Simple. That solves that problem. That solves that. I think my spelling of continuous is trash. Continuous. All right. So that solves the problem. Is this differentiable? Absolutely. Okay. That's the second one. Differentiable. Is G differentiable on AB? Answer. Absolutely. Following the same in instruction. F of x is continuous on AB. Absolutely. I mean, sorry, it's differentiable on AB. We've talked about that several times. And y, of course. I mean, y is also very, very continuous. I mean, sorry, it's also very differentiable. As a matter of fact, this is the derivative of y. That's the slope of y. Okay, we will get to that. So it's differentiable. All right. So because why? Because G is differentiable. I mean, sorry, F is differentiable from hypothesis, from the hypothesis, and Y is also differentiable. Being a straight line is also differentiable. So I'm saving this messy page, and so now those two things are clear. Now, G is differentiable, and G is differentiable on AX, as in on AB, and G is also continuous on AB. All right. Now the question is that why am I saying is AB? That's pretty much obvious since um, point A comma FA and points B comma FB are both, both transcend the the curves that generates f of a. What I mean by that is that we know that the curve, so we have it like that. This is f of x, this is y. Okay, this is b f of b, this is a f of a. Those are the coordinates, and this is going to be a, this is going to be b. So you can see that the curve, let me pick a different color for that. Come on. Okay. Let me pick this gray. This looks kind of lovely. All right. As you can see, this is this place and this place are covered by A and B, and the curve is between them. So we can see that therefore, and then the difference we are talking about. Of course, this is the difference that we are talking about. When we subtract A from B, what is left of it? That's those pockets in between it. Okay, so you can see those pockets are actually covered conveniently by the entire function. I actually cover those intervals that so we can now say that G is continuous on AB and G is continuous on uh, differentiable, sorry, differentiable on AB. So two of the conditions of two of the conditions that we need for Rose theorems are now covered. Continuity is covered by for G. Differentiability is covered also for G. Now the next thing is for G is do they have the same values? Does G have the same value at the origin? Is GA equals GB? Because um, if you go back to the statement of the Rose theorem, it says that A must be less than B, f of A must be equal to f of B, blah, blah, blah. Now we are testing it for G. Okay? Okay, let me just reel out the entire Rose theorem. That f must be continuous. If A is less than B, that is 1, then f of A must be equal to f of b, that is 2. F must be continuous, that is 3. I'll be on closed interval AB, that's 3. F must be differentiable on closed interval, on open interval AB, and that is 4. Now we have, of the 4, we have established 3. We have established, as in now for G, we have established that A is less than B. That's a standard. We have established that G is continuous on AB. That's also good. And we have established that G is differentiable on AB. That's fantastic. The last thing for us to establish is that GA equals GB. If you can establish that, it means that G will satisfy all the conditions, must have satisfied all the conditions for the uh, Rose theorem. So let's see what happens at the origin. So let's differentiate. Let's differentiate G first. You know that G x is in fact um, gx is in fact f of x minus f of a plus x minus a times f of b minus f of a over b minus a. That's actually aha. So now let's differentiate this. So g prime x will be fx prime. That's derivative, and this is a straight line. If you differentiate a straight line, you get its if, if you differentiate a straight line, you definitely get its you get its slope. That's him. All right, and now this is just take a good look at it. This is the C, because it's f of a, which is going to give you a particular value. That is, it's going to give you a constant value. And this is your x, and this is your n. So we are talking about y equals mx plus c here. So this m here is the derivative. So if you differentiate the whole of this bunch, it's going to be plus fb minus fa over b minus a. All right. So that establishes that. Okay. I think my canvas is messy, kind of. I think I can. Let me just save the canvas and move on to the next page. Mhm. So we have done that now, and we now want to test G at the origin and G at the end. When I mean at the origin, I mean G at A. What is it going to be? Would it give us the same value as G at the end of the line? Let's see. Let's see. So G, of course, is the simply put G at X equals F at X minus F at A plus F at B minus F at B over B minus A times X minus A. All right. So G at A, therefore, will give us what? If you That's F at A, of course, minus F at A, which is a constant, plus F at B minus F at what did I write here? This should be A. Sorry, F at A over B minus A. Of course, we are saying into A minus A. Well, A minus A is 0, so it's going to kill out everything we have there. So we are going to have F at A minus F at A, which is going to give us 0. So therefore, G at A is apparently 0. Okay, sorry about my handwriting. All right, G at A is apparently 0. Now let's try G at B. Okay, so G at B, of course, let's make it look gorgeous by picking a different color. Let me go kind of feminine now. I think our ladies like pink. Okay, let's see what G at B is going to be. Let me clear this one. Okay, so G at B will be F at B. What I'm doing is that I'm putting B into wherever I see X in that first equation, I'm putting B there. So F at B minus, so you open this bracket, F at A plus F at B minus F at A over B minus A into B minus A. All right, there's a B minus A here and there, so I can cancel out those two. So which means I'm going to have F at B minus F at A minus F at B plus F at A. That's my minus coming into to do justice. So everything cancels out and it's now 0. Therefore, G at B will be the same thing as G at A. So voila, we have satisfied all the conditions for Rowe's theorem. We have satisfied all the conditions for Rowe's theorem. And I'm saving this page now, and I'm going to come back to, we defined G prime at X. When we did the derivative, we had it as a F prime at X minus F B minus F A over B minus A. I hope you remember that. So let's just put this one like this. All right. So according to Rowe's theorem, according to Rowe's theorem, by Rowe's theorem now, by Rowe's theorem, there exists a C. Okay, if my function is continuous on AB, if my function is differentiable on AB, if A is strictly less than B, okay, and if f of A is equal to f of B, then there must be a function. Now G satisfies all those ones, so I can start talking in G form now by saying G is continuous at A, I mean, G is continuous at all over A, B. G is differentiable all over A, B. Of course, my A is less than B. And what else? My GA is equal to GB. All this we have established. Then Rowe's theorem says if all those things are established, then there must be a C between A and B, such that the derivative of the function we in question is going to be zero. The derivative of the function at that point C will be zero. So let's put that let's now translate that here. So we now have G prime C must be F prime C minus FB minus FA over B minus A. And it must give us zero. It must give us, let me clear that. It must give us zero. Okay. Okay, so what else? What else? We know that GC is zero, all right? So GC here is zero, all right? So which implies that F prime at C is in fact, so we just move this one to the other side, it's in fact FB minus FA over B minus A, which is exactly what we set out to prove in the Rowe's theorem. We want to show that there is a point between A and B such that the derivative of f along, at that point C will be the same as the gradient of a secant, that is a line that crosses, that's run across the entire length of the curve. And that's what we have just shown. We know that f of b minus f of a over b minus a is the gradient of that straight line that we drew earlier in the day. So that ends the class. I'm saving this page, and I want to write out your assignment now. Assignment. Okay. So let me change the orientation of your screen. And your assignments, if you choose to do it, assignments. Okay, number one, of course, you can guess, convert the video to a note. All right, number two, in precise, in clear VN, describe how the Rowe's theorem is the backbone of the proof of the of the mean value theorem. All right, so today is 23rd of March 2023. Dr. Adefokun TC signing out. Thank you very much.